Welcome, this is lecture number 21. In this lecture, we are going to talk about constant off-time control methods. So, in this lecture, we are going to talk about constant off-time control, some basics, and we have already discussed the modulation aspect of constant off-time. So, in this lecture, we are going to emphasize more on the control aspect. Then we will talk about single loop and two loop constant off-time control, then problem with constant off-time control and what are the solution. Then MATLAB case studies of a buck converter under constant off-time control, and then constant off-time feedback state feedback control. So, if we go to constant off-time control basics, so we will first recall our fixed frequency peak current mode control. In fixed frequency peak current mode control, we have a control current, and this is our peak current reference. This is our peak current reference, our peak reference. An inductor current is compared with the peak current, and then comparator output is used to turn off this reset or the latch circuit, and the turn on happen by the switching clock here. So, this is trailing edge PWM, under trailing edge PWM that we have studied, and this is under fixed frequency control. And this is the waveform under peak current mode control, where here we have a trigger pulse. In this case, it is a switching pulse which is used. So, in this case, it is switching pulse. The edge of the switching pulse turn on the switch, and the switch turns off when the current hit the peak current limit. Now, keeping the same analogy, that means we want to again control the peak current, we want to use constant off-time control. Here, it is the same as peak current mode control, but in this case the time period, instead of time period in PWM, this is our fixed frequency PWM. Here our time period was constant, that means you can see this time period was constant, but in this case our off time is constant. This is our off time, the off time is constant, okay. But the basic like a fundamental of controlling peak current, that logic remains same, but the fundamental modulation structure is different. And here constant off time, off time is constant, that we have discussed, but time period is not constant. So, any perturbation can actually change the on time. So, this is our control variable, because off time is constant and on time is generated from this comparator. So, that varies, and if that varies, then time period will vary, right. And here the trigger pulse that comes, which turn on the switch, that comes from the monoshot timer, because if you take this particular phase, in this phase, so here it is switching frequency is not constant, so it is TSW, okay. So, in this trigger pulse, this off time is generated from a monoshot timer. That means, when you enable the monoshot timer remains activated for the duration of T off, and once the T off time is elapsed, then the monoshot timer is turned off, and based on the falling edge trigger, we can turn on the switch. That means, the switch turns on when the monoshot timer finishes its counting, okay. So, that is the trigger pulse. So, trigger pulse is the falling edge of the monoshot timer, okay. Then the logic remains same, it controls the peak current. So, who generates the trigger pulse, that we discuss? The trigger pulse is generated by a monoshot timer. That means, here first it detects the positive edge, that means once the inductor current try to cross the peak current limit, this is my control current or the peak current, then the QC goes high, okay, and when the QC goes high, this edge detection circuit detect the edge, and this trigger pulse activate this monoshot timer, and as long as the monoshot timer is on, this is not, that means you have inverted the logic, because you have to turn off the switch, and this switch remains turned off as long as the monoshot timer is activated. When the monoshot timer turns off, that means finishes its counting, then we again turn on the switch. So, that is the logic, okay. So, this is the logic, and that we have discussed. The monoshot timer, whenever this hit the limit, the monoshot timer is activated, and when the monoshot timer finishes its counting, then this edge is used to turn on the switch. So this is known as constant on time off time current mode control, which is analogous to peak current mode control. And again we have discussed that here time period can vary if there is any perturbation in the on time. So here on time can vary when the converter operates, because it is not a constant quantity. Under steady state they will reach more or less constant. So both technique in peak current mode control for fixed frequency and the peak current mode control like constant off time, they control directly the inductor peak current. Now what is the basic logic? Instead of current we can also compare voltage, okay, or you can take the combination of current and voltage. So if you take two signal x1 and x2, and if whenever the x2 is higher than whenever x2 is higher than x1, then this comparator actually goes high, okay, and whenever this happens, then this positive edge generate a trigger pulse and that activate the monoshot timer. So in case of voltage control, we will simply replace x1 and x2 by V0 and Vref. So that means whenever V0 is greater than Vref, then this output should be high, this output of the QC should be high, okay. For example, if the monoshot timer was turned off, that time the voltage will fall, okay. So voltage will fall, that means during the off time, and when the monoshot timer finishes its counting, then switch is turned on and the voltage keep on rising. So whenever voltage rises and it try to cross reference voltage, then this switch goes high, okay, and then this monoshot trigger pulse activate the timer. So if you take the voltage waveform, so this is exactly what I have discussed. Whenever the switch is on, initially voltage will fall, because if you draw the capacitor current, then you will understand that if you draw the capacitor current of a buck converter, so like this, okay. So whenever the switch is on, so this is, sorry, if I draw the capacitor current, so let us draw this capacitor current and we will demarcate this duration. Whenever switch turns on, the capacitor current is negative, so it rises, then it falls, sorry, it falls like this, again it rises, again it falls like this. So as long as the capacitor current is negative, the voltage will continue to fall, the voltage will continue to fall. Whenever the capacitor current become positive, voltage will rise. Similarly here, whenever this capacitor current is positive, then voltage will rise, when it is negative it will fall. So here the logic is that whenever switch is on, then voltage will rise after some time, and when the voltage crosses Vref, then switch turns off. That means this comparator goes high, and when it goes high, it activates the monoshot timer and the switch turns off. And when the switch turns off, after some time the voltage will start falling, and again when the monoshot timer finishes counting, then again switch turns on. So this process continues. Now there is a problem which we discuss in the context of constant on time. We have discussed what is the problem. That means if V2 dash, that means this voltage, after switch turn on, we found that means whenever the monoshot timer finishes its counting, then what is our expectation? That because switch was turned off during the activation period of the monoshot timer, so under steady state it is expected that output voltage should go below reference voltage, because the switch was off. But consider a scenario when you have a step down transient, when the output voltage is already high and your capacitor current is positive, so it will take some time to come to 0. During that time the voltage is high, it is much higher than reference voltage. During that time, even though you turn off the monoshot timer, the output will continue to become higher than reference voltage. So this can go up, this can be up. That means I am talking about the scenario when the low step up transient, the voltage will simply go up like this. and if it is high, then the comparator output is high, and that means it continue to remain high, and if continue to remain high, there is no edge detections, there is no edges, right. So the monoshot timer cannot be activated, and if the monoshot timer is not activated, that means switch remains on, because monoshot timer act is to turn off the switch, remains on, and the switch remains on, the voltage will keep on rising. So instead of, because it is step down transient, so you have to slew down the current, but instead of that, current will actually go up, and this process actually it takes the voltage to this input voltage, that means huge, it increases significantly, and the inductor current can saturate the core. Okay. So that means we have to be very careful about this constant of time. So what we have to do, we need to introduce a minimum on time. In case of constant on time, we have introduced minimum of time. In case of constant off time, we have to introduce a minimum on time, and that means we need to create a separate trigger pulse, and that we will discuss, which means we have to check the comparator status. That means if you take this QM, which is the output of the modulator, which was supposed to go high, which is supposed to go low, whenever the monoshot timer is turned off, that means QM should go from high to low when the timer actually it finishes its counting, and then it detects the edge, and that edge is delayed, and after the delay, and this delay actually we load with minimum on time, and if it find that after the delay the still QC is high, that means your output voltage is still higher than Vref, then it actually take this, it generate another trigger pulse. So this is another trigger pulse, and then it ended with the original. So we have used earlier this trigger pulse. Now here we are generating a falling edge trigger pulse, and which is a delayed signal, and this will take the OR operation of this. That means even if the switch output voltage is higher, it will check after the monoshot timer finishes its counting, and if it checks after some time it still remain high, then we have to forcefully turn off the switch. Okay. So that logic we will see when we will go to the MATLAB simulation. In single loop constant of time control, we can use both current single loop as well as voltage single loop. So in current single loop, if we want to control the peak current, and this is particularly important when you are going for a battery charger, right. So the battery charger, the voltage of the output voltage at the battery terminal, it is not in our hand, okay, because it is decided by, the battery is decided by how much current you are putting in the battery, and the terminal voltage of the battery will actually go up. So we do not have any control over it. But what we have to do, whenever we are, suppose if we take a buck converter and there is an output capacitor, and here you are putting a battery, this is your battery. So you have a positive and negative terminal of the battery. So this is my battery. So we want to make sure that this current which is going to the battery should be constant, and that can be achieved under steady state if we ensure that average inductor current is same as the required battery current, because the capacitor average value should be more or less 0. Then we can, because it is slowly varying the voltage, then we can ensure that we can perfectly supply the average current which is required by the battery. And we can do it because this is a ripple parameter, right, and this ripple can be written in case of a buck converter. What is the expression of the ripple? If you write in terms of falling slope, it is M2 by T off, and the M2 is V0 by L. Now this V0 output voltage, what is the output voltage if you want to connect to a battery terminal? It is the terminal voltage of the battery, okay, and that you can measure, right. So by measuring the terminal voltage and assuming, because setting T off is constant, right, because you are setting the T off, and the inductor is assumed to be known, so you can find out T off by L. I am not saying it is exactly known, but it is reasonably known because it is set from the design. Then output voltage can be measured from the terminal voltage of the battery, and then if we know output voltage, then we can know what is my delta IL, right. So, what is, if you know the delta IL, then what you have to do, your required average current is nothing but my peak current, this is my peak current minus delta IL by 2, this is my average current, and I want to make sure that, so it is an indirect control of battery current by means of peak current, because we want to control the average current, but in order to control the average current, we are controlling the peak current. So, if we can make sure, if we can, that means this is the required average current, so the peak current can be found. So, this is given by the battery. So, this is my battery current, okay, this is my battery current, and delta IL by 2 I told that this will be calculated from here. Since voltage of the terminal of the battery is slowly varying, so it is more or less constant for switching time period, because it varies at a very slow pace, like battery terminal voltage, because converter can operate, is operating, let us say 500 kilohertz, whereas the battery terminal voltage varies in terms of minutes, okay. So, that means it is a very slow varying process, and under that slow varying, if you take the sample of the output voltage, so then you can compute the ripple directly by measuring the output voltage sample, and you can set the average value of the ripple, and then you can set the peak current. By that way you can control the average current, okay, and this is known. So, that means this is known, this is more or less known, and this we are taking the sample from the battery terminal voltage. This technique can also be used in LED driving. In fact, many commercial products use that. So, if you use a either boost or buck converter average current control of the LED, so you can use the constant off time control, because we will see in the subsequent lecture that constant on time as well as constant off time control has inherent current loop stability. So, whatever duty ratio you will take, it will always remain stable, unlike in peak or valley current mode control, where we will find there is a duty ratio range for current loop stability and you need to put a compensating ramp. Here you do not need a ramp compensation. So, you can very effectively control the average current by controlling the peak current. Okay. Now, we can also talk about two loop control. It is current mode control. So, similar to our traditional current mode control, we will have a outer voltage loop, and then this is the voltage controller, and this is our inductor current, and then after the inductor current, this is like our reference current, right? Reference current, this is our inductor current. Then output of the comparator goes to the constant off time modulator, and that we have discussed. It will also have a minimum on time. Then we can implement a current mode control. So, the biggest advantage here we will see in the simulation result, since the current loop is stable inherently, then there is no subharmonic instability problem, okay. And I will show you the supply transient as well as the current loop stability is very excellent, because supply transient even in current mode control is very good, but here since there is no stability problem, so you will not find any, almost no change in the output voltage, even though the supply can drastically vary. So, I want to show you the MATLAB implementation. So, again it is a two loop control, current mode control. So, this is our inner current loop, this is our reference current which is coming from the outer loop, and this is the block diagram which I have shown for many simulation. The overall block diagram, this block is the converter power stage and it is driving a resistive load, right? We have discussed that resistive load, but we can also add a constant current load. So, like we are, because if we want to apply a load transient, we can apply a constant current load. In fact, we can also apply a constant resistive load also. So, you can program this, and this is the actual load current which is going to the converter. Now, this block, what is this? So, if you go inside this block, this is the transfer function where we can set the compensator, because this is this compensator that we talked about, and you can see this reference block is nothing but our this block here, which generate the error voltage, okay. And here we are using the inductor current. So, here this is like our IREF and this is our IL. So, these two are compared and we have discussed this is IL, this is IREF, okay. Then this is our comparator that we have discussed. So, this comparator is nothing but this comparator. Okay. Then this whole block is our constant of time modulator. So, this block is our constant of time modulator, and the first block will be the edge detection circuit, which is here. Then it will have a minimum on time logic and the OR gate, although we put separately, but actually this is the OR gate. So, this gate is here. Okay. And only this block inside it is there, and if you go inside, this is the block. So, here it takes the negative edge, that means this is my QM analogous to this, and this is my QRC which is coming from here. Okay. This is the AND gate which is here, and the delay block, this is the edge here, and the delay block is implemented using this combination, the delayed block, and here we are setting the minimum on time, Okay. So, if you go, okay, so this block is a monoshot timer because we are delaying by the time value. Now, if you want to do precise current, average current control, which we have discussed, we can set a reference current which we need to control, but ultimately it is constant of time control where we are controlling the peak current. By controlling peak current, we want to maintain the average inductor current to its desired value, which is Iref. So, V0, if suppose if you take a buck converter where the inductor is connected at the output terminal and you want to control the current, it may be LED driving application where the terminal voltage which is connected with the buck converter is a LED string voltage, which it will be known because it consists of the forward voltage drop. Okay. It will be reasonably known. Okay. Then T off. So, you can calculate peak from this equation. Okay. And then we can implement this logic because this will be more or less known from the LED string. This will be set by us, and this is our inductance value, which we are assuming will be more or less known. There will be certain variation in the inductance value, but we can actually adjust and we can make that reference current, inductor, by controlling the peak current we can more or less maintain the average inductor current to its Iref value. And that means we need to precisely control average current, because if you go to traditional average current mode control, which required to, you need to put a very low bandwidth current controller in order to extract the average current from the inductor current. So, that will slow down the bandwidth of the current loop. But in this technique, there is no as such averaging method is to extract the average current, or neither we are applying any low pass filter. So, it is the sense current which is the actual inductor current, and you are applying a peak current logic, but you still can obtain the average current control. Okay. So, this LED driving we can say monoshot timer, all these blocks are known. Now, if we want to control the LED nominal current, then we need to set the peak current accordingly by setting the terminal voltage of the LED string voltage. But one thing I have not mentioned, this works fine for analog dimming of the LED. But if you go to PWM dimming, or in that case the current, the LED string is getting connected and disconnected, that only by controlling current will not be sufficient, because during connection and disconnection phase, during that, like we want to connect the LED string and also we want to disconnect. So, during this process of connection and and also removing, the voltage overshoot undershoot in the capacitor can cause a significant flickering current, and in many cases it can damage the LED. So, we need to consider some other aspect, but for analog dimming this technique will work fine. So, I want to show few simulation case study like a supply transient performance and the current loop stability. So, here I am taking output voltage to be 1 volt, okay, but input voltage I am changing from 12 volt to 2 volt, right. Even you can go further down, and I am using a compensator, outside compensator. In typical current mode control, if you go to 2 volt and close the loop, you will get severe instability. not only the just current loop, because we know current loop stability problem occur at 0.5 duty ratio, but due to closed loop the instability problem can be really severe. So, you need to add ramp compensation, but here we are not going to take ramp compensation. So, here I am just talking about, that means I am changing the supply voltage. So, this control parameter I am just calling the parameter file of the buck converter. I am setting reference voltage to be 1 volt, my initial input voltage is 12 volt, and I set the load resistance to be 1 ohm. So, you can ignore all these quantities, these are all redundant, not necessary. Okay. Even the duty ratio may not be needed. So, sorry, here you need input voltage 12 volt, reference 1 volt, and load resistance is 1 ohm. You can change it, and I am setting a PI controller where Kp is 80 and Ki is this 2.5 0.25 into 10 to the power 6. Okay, and then I can load this controller to the actual simulink, that I will show you. And here I am taking the total simulation time of 5 millisecond, and I am applying a step transient at 3 millisecond. So, I can remove this quantity 3 millisecond, and here it is not needed, this is not needed. Now, I am applying a transient of minus 10 volt, that means initially it is 12 volt, at 3 millisecond time I am applying a minus 10 volt step size. That means, if you go to the converter Simulink diagram, and if we check the Simulink block diagram, I will show you that in the block diagram. So, this is a supply step which actually we are applying with a T step, and this we have discussed in the previous lectures, this block diagram. Now, if you go to constant of time, so this controller is directly called from the .m file. Okay, and the on time, this is the minimum on time, T on minimum, that we have discussed, and this is the off time, and this on time and off time are calculated from this file. That means, we are setting this on time is simply V rep by V in into T, and off time is T minus T on. Okay, and then we are running this simulation. So, here what I am doing, I am first running this. So, loading the parameters. So, now the parameters are loaded. Now, I am running the simulation. So, if I run the simulation, then if I go to the plot command, it will show the plot command, what waveform are we going to show. We are going to primarily show the inductor current waveform and the output voltage waveform. Sorry, this is the reference transient, I am sorry. So, I need to change. Okay, so I am initially showing supply transient. Okay, so let us show the supply transient where the input voltage changes from 12 volt to 2 volt. That means, there is a change of 12 volt to 2 volt. So, very low input voltage. Okay, so you will see there is no change in the inductor current. So, we have applied the supply transient here. So, this is the point where applied the supply transient. If you see, there is a drastic change in the switching frequency, because here we are talking about constant off time, and if you recall, in constant off time we are familiar that what is the current ripple, the inductor current ripple, if we take the falling slope, it is V0 by L into T off, right. Since we are using closed loop control, so V0 is maintained. That means, I am getting this whole quantity is constant, this we are setting this T off which is constant. I am taking a constant value of inductor, and I am regulating the output voltage. So, this quantity is constant. That means, even if we change the supply voltage, the output inductor current ripple is not supposed to change, it will remain constant, but it will definitely change the switching frequency, right, and this is exactly happening here. So, you can see before transient, this is the waveform where your duty ratio is pretty low, you can check from here. The on time compared to the total time is low, because if I take the cycle from here to here for the close, so it is very low duty ratio. But if you go after the transient, that means, if you go here, you will find after transient, if I take this, the on time is pretty large compared to off time, because here like a 50% duty ratio, that means your output voltage is 1 volt and input voltage is 2 volt. So, you can further reduce, there is no problem. Okay. Another part I want to show, if I go to the output voltage response. Okay, so if I go to the output voltage response, if you just take the few cycles, you will find there is almost insignificant change in the output voltage, because 1 volt is my output and it is more or less 1 volt, because this scale is just 0.005, 5 millivolt. So, there is a like a 4 to 5 millivolt change, and you can assume that there is no change in the supply voltage, that means supply remains more or less constant. So, there is no change in the output voltage remains more or less constant, but we have applied a supply transient of from 12 volt to 2 volt. Okay, that means this, and there is no ramp compensator. So, you are getting excellent supply transient performance. In fact, this is also consistent in peak current mode control, but in peak current mode control the current loop will become unstable for this duty ratio, and here you are also getting superior current loop stability. There is no problem of stability, even we are using a very high closed loop gain, it is not at all, I mean it is perfectly stable. Now, we want to see load transient performance. So, if you go to the load transient performance, now what we want to do, we want to change the load from 10 ampere, let us say we are changing from 10 ampere, it was originally at 1 ampere load, now you are changing to from 1 ampere to okay. So, you applied a load transient, let us see. The load is changing from 1 ampere to 1 plus 10, 11 ampere, okay, and you want to see the transient performance, step up transient performance. So, we need to increase the gain, because the current mode control is a problem, because it is an overdamped system. So, we need to really increase the bandwidth in order to speed up the response. Okay. And if you check here, okay, so it smoothly rises from this to this point, right, and you can also apply a 20 ampere load step. So, it is not a problem. But you see, an interesting point is that I have applied load transient at 3 millisecond when the switch was turned off, and when the switch is turned off under constant off time, the modulator will not respond to the load transient, because it will remain off throughout this interval when the monoshot timer is activated. As a result, from 3 millisecond to 3.0015, that means 1.5 microsecond, that means the total time period we are assuming we are trying to maintain at 2 microsecond. So, almost 1.5 microsecond is the delay. As a result, you will find that the undershoot is somewhat large, because here we have applied a load step transient, and since the voltage is going down, so it is going further down, okay, and that is why the transient response is somewhat penalized. So, if you want to consider a best case scenario, then I want to shift the load step transient a little further right side, so that it should not coincide during my off time. And if I do that, I will just show you that if I make it a little, if I shift it little bit, then I will show it the response can be improved significantly, because the delay can cause further undershoot, because your constant off time is not responding to that load transient performance, because yes. So, here if you see, if you go to the inductor current waveform, so I want to show that the inductor current waveform, here we are again we have applied load step. Where did I apply the load step? We applied 3 millisecond plus, okay, so I need to apply a little further. So, that means it should be t by, so it should be close to t, 0.9 start t. So, I am shifting the load transient further, and then that means it is just the adjustment, so that every modulator, whether you take peak current mode, valley current mode, so the modulator will have an inherent delay, and if you can, if the load transient, so here we have little bit shifted the transient response, that means, so it is almost responding because a load step transient happen. What time have you applied? We have applied the load step. If you go and check this point of transition, so it is happening when the switch is about to turn on, that means it is happening around 3.0016, and if you go to this part 3.0016, so 3.0016, that means it is during the on time. So this is the best possible transient scenario that you can achieve in this case. So we understood the load transient performance. The next part is the reference transient performance. So if you go for reference transient performance, that means now we want to apply a reference step change, whereas the load is kept the earlier load, and let us run it. So here we have applied a reference step change of 0.1 volt. It is changing from 1 to 1.1 volt. So let us see what happened in the transient response using constant on time control. So here you will find that output voltage reaches from one step to the other state almost in one switching cycle. That means, if I zoom this portion, the output, the inductor current slew out very rapidly and then it comes back. So that means this is somewhat close to optimal response, that means not exactly optimal because there is a switching event here. So we can further improve the transient part. This is one of the very close to time optimal performance, but it is not exactly because there is another switching event. So by that way we can improve the step up recovery very fast. Now we can use state feedback control, we can implement using constant off time modulator. That means if we take Iref IL, this is my error current and this is my error voltage, then you can set the suitable current and voltage gain, and then we can use this logic and then we can go to the modulator, and this can be tuned. We will see in subsequent lecture at the end that we can even apply some sort of suitable choice of current and voltage gain in order to obtain fastest transient response, which is a time optimal response. So we have discussed single loop and two loop constant off time control. MATLAB simulation of constant off time control was discussed. Then we have also discussed minimum on time in constant off time control. Then we have also discussed about average current control in a buck converter, and we have also discussed constant off time state feedback control, and we have shown some performance study using MATLAB simulation, that also we have demonstrated here. So MATLAB simulation we have considered, and we have seen that the constant off time is analogous to peak current mode control, but at the same time there is no current loop stability issue. So with this I want to finish it here. Thank you very much.